This week in class, we're going to be looking at work and energy. The big takeaway from work and energy is that when you do work, things get done. The study of work and energy is a different way to look at how we model and understand motion. We've seen this problem before. Bob pushes a box with some force F. We draw a free body diagram, including the normal force, the weight, the force of Bob, and friction, and then we sum our vectors. Once we've summed our vectors, we can create the equations of motion. From the equations of motion, we find the acceleration, and we can plug the acceleration into kinematics to determine the motion of the box. To look at this problem in the context of work and energy, we need to know something about the path, S, the direction and distance the box is going. Only two forces have any vector components that point along S, the force that Bob pushes with, and the friction. The work done by any force is the dot product of the force and the path, that is, the components of the force that is parallel to the distance traveled. In this case, the total work done to the system is the work done by the force that Bob pushes with, minus the work done by friction, all multiplied by the distance s that the box traveled. The normal force and the gravitational force do no work at all. The other half of work and energy is the kinetic energy. Every object that's moving has a momentum, which we define to be mass times velocity. Let's plot that. On a momentum versus velocity graph, an object that's speeding up makes a curve that looks like this. The slope is the mass of the object, and the area under the curve is 1/2 times the mass times the velocity squared. This area is called the kinetic energy of the system. The punchline is the work done to the system is equal to the kinetic energy change between two different velocities. That is, work is 1/2 mv final squared minus 1/2 mv initial squared. This is known as the work energy theorem. Let's put this all together. We know the work done by Bob and friction over the distance s. Work is equal to the change in kinetic energy, so putting these two together gives us an equation that we can solve for the variables that we're looking for. So now we have two ways in which we can model motion. With Newton's laws, we start with forces, derive an acceleration, and then plug that acceleration into the equations of kinematics. With the work-energy theorem, we start with forces and can go directly to kinematics through kinetic energy. The work-energy theorem might seem easier. There's only one equation. It doesn't look like there are any vectors. Well, the last part's not true. You still have to find which force vectors point in the direction of motion. The work-energy theorem does not replace Newtonian mechanics that we learned previously. It augments it. So let's get going and let's learn about work and energy this week.